Hello, hello. So today we've got quite a bit of work. Yeah, so we are going to work on sorting algorithm. We are going to talk about bubble sort, bubble merge sort. We are going to compare this algorithm. We are going to have a look at two examples for each bubble sort and merge sort. We'll see the definition of complexity. Yeah, why we define that some of algorithm has complexity n squared, some n log n. So let's start our session. As I mentioned before, we are going to work on bubble sort, on merge sort, and we are going to compare these two sorting algorithms. We'll start with the definition of what they actually are. So sorting algorithms actually are. So this is some algorithm that help us to redefine our data, to redirect our data, to sort it in some specific way. Basically rearranging elements in a sequence. In either ascending or descending order. Sometimes there are other orders. For example, when we are going to talk about some more complicated problems, we can sort a list of, for example, by length of the word from the longest to the shortest one or other way around. And why they are important. Yeah, so they're basically fundamental in terms of what, as I mentioned before, implementing and rearranging data, optimizing data, retrieving data, passing data. Here we can see example of red one unsorted array and blue one sorted array from in ascending order. First sorting algorithm that we are going to work on today is going to be bubble sort. It has this very interesting specific name, and the concept of bubble sort says that we are going to take two elements and put them together in kind of bubble, and we are swapping elements inside of the bubble if they need to be going in ascending or descending order, depending on to what order we defined. Main key point here, it works well for small data and it has complexity O(n) squared. We will come to this definition in the end of this lesson. And this is an example how we can combine two elements of a sequence in one bubble. So now we are going to have a look at the very first example, which says that we have unsorted list of numbers. I selected 8 numbers, and we are going to sort the elements using bubble sort. So now let's switch our exercises. We are going to sort the next list. When we have initial list, elements 38, 4, 51, 23, 9, 65. So how we are going to handle this problem? I, for example, prefer to split the table into, I will use table for showing how I'm working this out. We will need to understand the difference between pass and substep. We will quickly go through all of them. Action, what action is, and resulting list. So the very first step, let's say we are going to sort our list in ascending order. So we can see from this list, the very first element would be what? 8, and the very last element would be 65. So what would we do in this case? The first substep, let's get rid of a bold font here. We compare the next numbers. We need to compare 34 and 8. And do we need to swap these two elements? Again, as we mentioned before, we are sorting lists in ascending order. So we need to swap these two elements. Then, how does our list change? Instead of 8, we are going to have 34. Now, to complete the full pass, so again, the full iteration from the first element of the list until the end, the last element of the list. First element is 1. Thank you so much. Thank you for correction. Yeah, first element would be. So how many sub-steps we would have? So at each iteration, we can see we would have 1, 2, 3, 4, 5, 6, 7 sub-steps. Yeah, because we are comparing, we have 7 pairs of comparison. So the next, after we swapped 34 and 8, now we are going to compare 34 and 50. Okay, let's compare 34 and 50. Do we need to swap anything? No, we are writing no swap. the list is staying the same. Now, we have already compared 34 and 50. Let's even highlight the elements that we have compared at each step. Yeah, so it was 8 and 34. In this case, it was 34 and 50. Now, the next list that we are going to compare, it's going to be what? 50 and 1. Do we need to swap them? Yes, we do. Because 50 is obviously larger than 1. So 1 and 50. Then, next pair is going to be 50 and 23. Do we need to swap elements here? I will skip a few steps here. They are quite obvious. So I will go straight away to the last step. Okay, so at the fourth step, we were comparing what? 23 and 50, and for some reason, did we swap it? No, we were not supposed to. Yeah, we were comparing 23, 50. We swapped them. Then the next thing that we were comparing was 50 and 9. Then we were comparing what? 50 and 65 that we did not swap. And the last step or sub-step, whatever you prefer, it was 12 and 65. So it was the first pass. Quite often during your exam, you are going to be asked, show all steps for the last pass. So this was the end of the first pass. So how many passes do you think we are going to have here to complete all of these? So we don't know yet how many passes we are going to have until we complete all of the steps. So now let's quickly move to the second pass. Let's have a look at the second pass. Yeah, we start over again. So we're going to compare 8 and 34. Then nothing is happening because they already sorted 1 and 34. We are swapping them. 23 and 34. Again, we are swapping them. Then 34 and 9. We need to keep them, swap them. 34 and 50, they are staying the same. 50 and 12, swapping. And 50 and 12. And yeah, so 65 also we would have. There will be one more step here. What step was skipped here? It was step 7, compare 12 and 65. Do we need to swap it? 50 and 65, and here we have no swap. Okay, we completed 2 passes. Now, let's move to the next pass, pass number 3. Let's see what it would be looking like. The next, here we would have how many steps? We would have 3 steps. So this is the final resulting list that we had after second pass: 8, 1, 23, 9, 34, 12, 50, 65. We can see there are quite a few elements unsorted. 8 and 1, 23 and 9, 34, 12. So we start with obviously 1 and 8. We are swapping them. 8 and 23 and 9. Do we need to swap them? Yes, we do. 23 and 34. Nope, they are already sorted. Now, 34 and 12, they are not sorted, so we need to swap. Yeah, I will skip steps for 34, 50, 50, 65, because it's going to be the same. And now we can see the only thing that is not sorted in our list is 23 and 12. So, let's write down the last pass. And this is very important for you, for your exam. In case if you are asked to write down all of the steps for the last pass. So what you would write down? Compare 1 and 8. You are saying no swap. Compare, what was the again? 1, 1, 1, 8. Let's take this one. So we compare 1 and 8. Then let's get rid of all of these. No swap. 9 and 23. Obviously no swap as well. And 23 and 12, or the matters, we would need to swap. And then you can show that 23 and 34, no swap. So you can stop here. Please be careful, don't lose marks on such a simple task. Here you would just need to show all of the comparisons, yeah? I'm trying to make it as detailed as possible because you never know how strict the person who is marking your paper is going to be. 23 and 12. After we swapped 23 and 12, we had 23 and 34. Again, just in case you can write down for 34, for 50. But in my opinion, it's not necessary because you already showed all of the passes for this case. So again, we have sorted in ascending order the list, the given numbers list. The next example that we are going to have a look at is going to be more interesting. As far as I can see, there are 12 numbers in it. Now we have 12 words in our list. And let's try to work it out. Let's try to work it out and let's swap to our exercise. Okay, let's have a look. Let's just have a look. So, in the beginning, we have apple, just apple and kiwi. So, first of all, how we are sorting words? Again, let's assume we are sorting it alphabetical order, starting from A, moving towards E. Yeah. In other way, we can say that in case if we are talking about ASCII tables, so we are moving from lower value to higher value. So apple and kiwi, what's happening? Nothing is happening. We are not swapping. Then we have what? Banana and kiwi. Here we need to swap them. Kiwi and apricot. We are also swapping them. So we swapped kiwi and banana. We swapped apricot and kiwi. We are swapping kiwi and grape. We are swapping and fig. So the first pass is quite simple. Here nothing interesting is happening. Kiwi and blueberry. We can see that our kiwi moved from the second position that it was in initial list to already position number 8 in the list. Okay. And we can also keep swapping it with what? With avocado, with avocado, kiwi and avocado. We are obviously swapping it. Kiwi and avocado. Now, the most interesting part starts right here. So we have pineapple, pear, and plum. Are they sorted? No, they are not sorted. Even despite they are starting from the same letter P, we need to have a look at the second letter, which is E and I. So which letter should be first? It obviously should be E, not I. So that's why we would need to swap pineapple and pear. Let's write down, compare that pineapple and plum. They are already sorted because they are sorted, but there's second letter. Now, let's finish. You can try, while I'm typing here, you can try to figure out how many passes we would have. The approach is same as before. I'm going to simplify now the steps. I will show you first 2 steps for the second pass. 6 we said, yeah. So when we compare banana and apricot, we obviously need to swap them. Then I'm going to skip it to the last step here, which is going to be write down 3 dots. And now for this step, let's have a look at the third pass. Actually, the first 2 steps of the third pass. We are going to compare apricot and apple, which is quite interesting because now we've got 2 same letters that are matching. A, B, B. So how we are going to compare them now? Now we need to have a look at the third letter, which is P, and we know that in alphabetical order P is going before R. So it means apple must go before apricot. By the end, fig and cherry. So now here we compare apricot and banana. I'm going to write down 3 dots here as well. And as you have already figured it out, by the end of the third pass, what we are going to have, and you can correct me, but as far as I can see, it must be apple, apricot, banana, blueberry, cherry, fig, grape, avocado. Nope, not correct. Let me have a look at the list again. What it was? Avocado. Yeah, we will swap banana and fig. No, banana and fig stand the same. Fig and blueberry, I apologize. Then we sweep fig and cherry. Then we sweep cherry and avocado. And that's all. Anyone can write down the full list for the third pass. What we will get in the end. Banana, fig, blueberry. Yeah, so blueberry is moving before fig. Then cherry and avocado are being swapped as well, as far as I can see again. Maybe I made a mistake. Please feel free to correct me. Apple, apricot, banana, blueberry, cherry. I agree. Cherry and fig, grape, kiwi, then pear. Yeah. To be to the end. Why kiwi is supposed to be swapped to the end? K is less than P as far as I remember. Yeah, Ramen is saying that P is larger than K, and I 100% agree with that. Q and K, no problem, okay? So we are moving on. So it was the end of the third pass, yeah? We are finishing passes, Kajanan. We are finishing passes. Now let's add a few rows to finish passes. So now let's move to pass number 4. Again, the same thing is happening, no swap. And how would it end? Let's say 3 dots here again, 3 dots here again. So in the end of the third pass, we've got apple, apricot, banana, blueberry, cherry. What else do we need to swap? We would need to swap avocado and cherry. Obviously, we are swapping avocado and cherry. And A, B, C, D, E, F, G. That's all correct. What the question, pineapple swap with pear. Pineapple and pear, we swapped it here. We even discussed swapping it, but for some reason, stop this step. Where did we lose it? Compare swap. So that's what we did here, and then we lost by copying and pasting. Yeah, so please be careful. Don't make my mistake. Don't copy and paste everything. Be very careful when you write everything down. Obviously, you're not going to have copy paste. That's done. And so it would be the end of the pass number 4. Banana, blueberry. And how many more passes would we need? There was a version here that we would need just 5 passes in total. Let's see if it's true. So the pass number 5, the same beginning. And by the end, we would definitely start with open blueberry and avocado. And that's pretty much it. We can't swap anything else anymore. Avocado and blueberry. Can we swap anything else? Blueberry, cherry, fig, grape? Nope. And now, pass number 6. Pass number 6. And in the end, we finally get all sorted out. Apple, apricot, P are all correct. V is going after P. That's why avocado is going after apricot. Banana, blueberry, A before L. Cherry, C after B. Fig, F after C. Grape, G after F. Kiwi, K after G. Pear, because P goes after K. Pear before pineapple, because I is going after E. Plum, because L is going after I. So how many passes did we have here in total? We can easily 6 in total. So in case if you are asked question how many passes you would have, you are just free to say that you've got just 6 passes. So this was pretty much it about bubble sort. So you can see how many steps we've done and how many steps we skipped just to sort all of them. The next thing that we are going to talk about is going to be merge sort. So what is merge sort? So this concept is about dividing and concurrent algorithm that breaks the list into sublists until we get single elements, and then we start sorting them all together. And then we merge them all back. Main key point that it's working better, way better for larger data sets, and the time complexity is going to be n log n. Again, we're going to talk about just in a tiny bit. And this is some kind of an example of what it would be looking like. Some people prefer to write down step by step. Again, it's up to you. Now, we are going to have a look at the same example that we had above. We are going just to change it a tiny bit. I changed the order, but it's pretty much the same. So let's go back to our exercises. So what we have now, we are going to be 23 here, 1 here, 50, 12, 65, and 9. That's how I want it to be. In certain way, we can say that merge sort is decomposition because we have one large problem here, which is our list, and we decompose, which is kind of correct, into smaller parts and try to work out all of these parts separately. So it's a good approach to call it decomposition. We are going to use a recursive approach here to solve the problem. So you can say that this includes decomposition as well. What I suggest us to do, we are going to copy this table from bubble sort, but we are going to make some changes here. We are, instead of substep step, what comparison we are doing here, action and current state instead. So this is the initial list that we had in the beginning. 34, 8, 23, 150, 12, 65. And what do we need to do with this list? We need to split it into two parts. Let me even highlight how I would split it. So obviously would be the right. And then we would keep splitting it left, right, and then sorting it. So what we are going to do, let's write it down. For the first pass, we have our initial split, which is the first step. We are, let's add input comparison, because it's not just a comparison that we are doing here. Let's make everything smaller to fit it. So what we are going to do at the second step, we are going to have for list coloring. So we would have for list. We keep splitting it into parts. So what would be these two steps? Again, we are splitting it first pass, but we are going to split left and right parts. So we would have 38, 34, 8, 23, 1, 51, 65, and 9. Now we are going to have the final split for all of them. Final split happens when we are splitting all of the elements into lists or arrays, whatever you prefer, of single elements. So in this current case, we are going to have 8 lists with single elements. It will be the end of the first. Now, at the second stage, we will start after this. Again, we split everything into 8 elements, individual elements. Let's also add one more list here to show. We can't split it anymore. So now we need to start merging it and merging it in a certain order. So we are going to compare the pairs that we have, and we are going to merge them into lists of 2. What are going to be these 4 steps? Let's have a look. So the first thing, we are comparing 34 and 8. So we need to compare them, and we say that 8 is smaller, 8 is smaller, so we are swapping it. Then we are comparing 23 and 1. We know that 1 is smaller, so we are keeping 1 and 23 in this. Now we are comparing 50 and 12, and again, 12 is smaller than 50. So we need to kind of swap them. Next step, 65 and 9, and again 9 is smaller. So now, from this list, we came to the next list. from these four lists, we came to 123, 1 and 59. And you might think that we are going to split it into singular elements again, but if we split it into single element list, there will be no point in carrying on because there will be nothing to merge it with. So what we are going to do starting from this step, now we need to keep merging it further and further into bigger lists. So after we sorted it, we can provide first merging. Let's do the merging. So what would be our first merge left? At left. Let's write down all 4 steps for merging at left. So now let's have a look. We have 12 and 50. We have 8 and 34. And 1 and 23. So what we need to do, let's get rid of all of these right part. Do we need it? No, let's keep it. So basically we have written down right part, which is here. Apologize, 965. It was 12, not 1, yeah? So let's keep the right part as it was, and we are going to fill the left list first of all. We need to compare first element from the left and first element of the second left, which is 8 and 1. What goes first? We compare 8 and 1. 1 goes first. Now, we need to compare 8 with the second element in that list, which is 23. Why are we comparing 8, not 34? Because we already know that 8 is the smallest number in this list. That's why we are comparing the smallest number with elements of the second list until we get, let's move to the next 4 steps about adding comparison. So left part is already sorted. We already know what's happening there. So no need to change anything. So, and we start, let me show you, right part. Let's write it down over here. So what we've got here, 1, 8, 23, 34. This is left part that is not going to change. Now we need to sort out right part. So we start comparing first elements of first 2 lists. That's at 12 and 9. We can see 12 is larger than 9. So we need to write down 9 as the first element. Now we keep moving to compare element 12 from the first list with element of the second list, which turned out to be smaller than the first one. Instead of 65, it could be 10 there. So what would happen in that case? We're going to have a look at this later. But we have 9 and 65 here. So we compare 12 and 65. So we write down 12 because 12 is small. Now we have 50 and 65 left. So we need to write down 50 because 50 is smaller than 65. And then we are filling the gap with 65 remaining element. No, it's not like bubble sort. Bubble sort compares only exactly 2 elements that are staying next to each other. Merge sort, as you can see, we are divide and conquer. Yeah? So basically the approach that Caesar used when he went to the north of France, dividing the elements which are listed in our case into smaller elements. And after we know how we can conquer them, how we can combine them back, we are combining them. So as you can see, we could, I'll change the example temporarily. Let's change the example to 9. And so we would just have 10, 12 and 50. Why would we add 12 and 50? We already know that the largest element in the second list is smaller than the smallest element in the first list. So we just put down all of elements of the second list and then all elements of the first list. So as you can see, it's not working like bubble sort where we are just swapping elements next to each other. We are taking elements from the group of elements and arranging them in correct ascending or descending order, depends what our task is. We would have final merge. We would have 8 more steps. So this, let's show all of the steps that we have left. So here we have the next list, 9, 12, 50, 65. Now let's go to final merge. And you might be curious, what would be the final merge here and how it differs from all of these previous steps that we have written down. Spoiler, there is no difference. We are using absolutely same approach. First thing, what we are doing, we have 2 lists again. First list, second list. We are comparing smallest element of each of the lists in the beginning, at the first step, which is 1 and 9 in this first case. 1 and 9. Then the next step, which is going to be, we are comparing next smallest element in the first list to the smallest element in the second list, which is 8 and 9. Still, we have just first 2 elements of the first list. We compare 23 to 50, as you can see in these 3 steps. So we step by step add 9, 12, 23, but we are not adding 50 yet. We are comparing now the last element that's left in the first list, which is 34, to the elements that are left in the second list, 50 and 65. 34 to 50, 50, and obviously 50 and 65 are both larger than 34. We are just adding remaining 65. That's pretty much it. So in total, we've got just 27 steps to compare all of the elements in this list. Now let's go back to our bubble sort. Let's see, 7 and 7. It's already 14 and 5, 19 and 5, 24. So you can ask me, what's the difference? Bubble sort is more efficient for this case. The point is, we were lucky that we just needed to make just 24 steps. Now imagine this situation. Try to answer the question, how many steps in total we would need to do. Let's see how many elements we have. Again, we have 8 elements. So before we had 7 elements for bubble sort. And we can use the next interesting trick that says number of passes is equal to ln of LST minus 1. So in case if we are going to have 7 elements, let's use numbers. It does not like the spelling. Number of numbers in the list minus 1. So we have 8 minus 1, which is going to be 7 passes. But the largest possible amount of steps, largest is not a good. Okay, the worst possible amount of steps, we call it the worst step, is going to be power of 2. Why would it be to power of 2? Because first pass, what would we do at the first pass? We would go 8 with 7, with 6, with 5, with 4, with 3, with 2, with 1. We would go through all of these number of steps. So it would be, how many steps? 7 steps. Then we would compare 6 to 7 to 6 to 5 to 4 to 3 to 1 to 8 until we move all of them. So this is called, or usually called, complexity length from number squared, or n squared, where n is the number of elements in your list. So let's go back again to the important thing that I showed you in the presentation. Where is it? Our presentation. So we can see I was saying that time complexity is O n squared. So when we speak about time complexity, we usually speak about the most complex case that can happen. And we are going to have just 3 passes. How would we calculate number of passes? Log from length number of numbers. Usually when we say log, we take log t, basis t. I believe you're already familiar with logarithms. So in this current case, it would be equal to 3. So we can see already we have less passes. And then worst possible amount of steps in this case would be log 2 len numbers. So this is not the question that you're going to have during your GCSE exam, but I'm just showing you how it would be working, the concepts, and why would merge sort be more efficient for large data steps, for largest. Let me show you. It just, let's call it programming definition, syntax sugar, and asymptotics. Yeah, this is the way we show the complexity. You can say complexity is going to be n squared, but in programming, we just show O from n squared. So, and here time complexity is going to be n log. Let me show you why merge sort is going to be more efficient. Let's say the first function that we would have, fx, is equal to x squared. And second function, gx, would be equal x times log x. So now let's see performance for a few elements, like 1, 2, 3. So let's say I have 2 elements. For bubble sort, it would take, let's say, 4 seconds in the worst case. For merge sort, it would take less than 5. But the further we go, you can see, let's say I have database of a school, 1,000, let's say how many, 800 students. So you can see how low the value of what? Of merge sort would be in comparison to bubble sort. Let's say f of 800, and this is j from 800. So let's see, you can see performance of merge sort for large data is almost 300 times more efficient. So now let's have a look again at bubble sort and merge sort and the comparison. So as we mentioned before, they can be used for any kind of data sets, data types. Time complexity, as we showed, for bubble sort it takes O from n squared. For merge sort it is n log n. Bubble sort is efficient for small data sets that are going up to 8, 10, maybe 15 elements. Merge sort, one more mistake, it should be large data sets only. And implementation of bubble sort is simple, of merge sort is slightly complex. I was thinking about writing pseudocode and Python code for you, but I want you to try to practice it as your homework. I will also post it as notes. So today, what we were talking about, we understand the difference between bubble sort and merge sort. We understand the importance of iteration, how these passes work, what iterations we use. We discussed the time complexity, what time complexity is, how it works, and its practical application. Next time, we are going to finally start working on Python, and we are going to cover primitive data types, casting between data types. Maybe we'll work on input, we'll solve a few problems on this. So thank you for your attention and for being here today for this session. Feel free to ask any questions.